In this podcast episode, Stefan Burns explores a broad spectrum of topics connecting Earth sciences, solar activity, ancient history, and cutting-edge scientific inquiries. The discussion weaves through the nature and impacts of solar storms, geomagnetic phenomena, archaeology, geophysics, and interdisciplinary approaches to understanding our planet, climate, and cosmic environment. Stefan shares insights into how modern science interprets these phenomena, what ancient structures might signify, and how emerging ideas challenge existing paradigms. Stefan opens with debunking exaggerated fears surrounding solar flares and coronal mass ejections often seen on social media. These events, while epic in scale, do not necessarily herald imminent cataclysms. The 1859 Carrington event remains the most significant recorded solar storm impact, which caused telegraph disruptions but no technological meltdown since modern infrastructure was non-existent. Since then, other notable solar storms occurred in 1872, 1921, and a close miss in 2012. The solar maximum in May 2024 saw moderate storms, such as the Mother's Day storm, that while impactful, were considerably weaker than a Carrington-level event. Stefan explains the concept of a superflare, an enormously powerful solar event, potentially 10 to 100 times stronger than known historic storms, which remains hypothetical as such an event has not been definitively observed to impact Earth. Should it happen, it could produce effects akin to a massive electromagnetic pulse, EMP, damaging satellites by causing dielectric charging and increasing atmospheric drag, leading satellites to decay rapidly and re-enter the atmosphere. Power grids might suffer localized blackouts, but a total global blackout is uncertain. Preventative hardening efforts have moderated impacts so far. The Earth's magnetic field is central to shielding life from high-energy particle radiation. Stefan explains that Earth's magnetic strength is exceptionally strong compared to Venus, Mars, and Mercury, which lack global or robust magnetic fields. The South Atlantic Anomaly, SAA, stands out as a region where the magnetic field is notably weak, roughly a third the strength elsewhere. This anomaly, centered near Brazil, allows more cosmic and solar radiation to penetrate, impacting satellites passing through. Though real-world effects on biology are unclear, this weakened zone contributes to challenges in satellite operations. The SAA's evolution may be part of a geomagnetic excursion or precursor to a full magnetic reversal, where the magnetic poles flip. Stefan notes the geomagnetic poles move at surprisingly fast rates, up to 40 kilometers per year for the northern pole, and excursions exhibit reduced dipole strength with more chaotic magnetic field configurations. During these times, multiple and sometimes temporary magnetic poles emerge worldwide, and the field weakens significantly, increasing surface radiation exposure. Stefan defines geophysics as the study of physical processes on Earth, encompassing seismic waves, magnetic and electric fields, and their interactions with space weather and biological rhythms. He emphasizes the electric currents induced by solar storms, which travel through the crust, oceans, and atmosphere, creating a complex, multi-layered energetic system. These currents influence phenomena such as lightning and weather patterns, suggesting Earth is far from a passive entity. Ancient sites, often located precisely where electrical energy concentrates, may have been selected due to an intuitive understanding of these geophysical properties. His journey into geophysics began through geology, and his curiosity led him to study the space environment and solar-terrestrial interactions. This broad, interdisciplinary approach allows better grasping processes unfolding over immense timescales, challenging simple reductions of complex environmental dynamics. Stefan explains geophysical exploration techniques like marine seismic reflection and ground-penetrating radar. GPR uses electromagnetic waves to probe just beneath the Earth's surface, ideal for archaeological surveys and infrastructure detection. Variations in ground materials, moisture levels, and frequency choice influence penetration depth and resolution. Marine seismic methods deploy sonar pulses and hydrophones to map subsurface structures under the ocean, crucial in oil and mineral exploration. Cross-validation using multiple geophysical methods, such as gravitational, magnetic, and seismic surveys, increases confidence in subsurface interpretations necessary for drilling or archaeological excavation. He highlights a professional example where GPR helped locate Webu-2 remains in California under challenging soil conditions, underscoring the technique's precision. The episode delves into Earth's magnetic history using proxy data like cooled lava flows, sediments, and fired pottery that preserve the intensity and orientation of past magnetic fields, archaeomagnetic data. Miyake events, dramatic increases in cosmic ray-produced radioisotopes like carbon-14 and beryllium-10 found in tree rings and ice cores, suggest sudden influxes of radiation, possibly from supersolar flares or cosmic phenomena such as gamma-ray bursts. Notably, a major Miyake event around 774 CE and others indicate these are rare but impactful occurrences. These events might cluster in time and relate to known climatic or extinction episodes, such as links proposed between geomagnetic excursions and surges in cosmic radiation contributing to major biological turnovers. The Earth's strong magnetic field arises from internal geodynamo processes powered by the planet's active geology and heat flux from its core. This contrasts with Mars, lacking a global magnetic field due to geological dormancy. Mercury possesses a weak field, and Venus has none. Stefan discusses proposals for artificial magnetospheres to protect future Mars colonies. Comparisons extend to gas giants like Jupiter, whose immense magnetic fields and radiation belts far exceed those of Earth. Jupiter's volcanically active moon Io and its plasma output generate intense radiation environments and influence the heliosphere with detectable Jovian flux, electrons reaching Earth periodically. The podcast unpacks space weather as the dynamic flux of charged plasma and magnetic fields streaming from the Sun, constantly interacting with Earth's magnetosphere. Plasma, the universe's most abundant state of matter, produces complex magnetic phenomena and energy acceleration processes observed around planets and stars. Solar wind, solar flares, and coronal mass ejections inject energetic particles into Earth's plasmasphere and radiation belts, influencing geomagnetic storms and induced currents on the surface. These effects can modulate atmospheric conductivity, influence lightning rates, and potentially trigger geological events such as earthquakes and volcanic activity through poorly understood electromagnetic coupling mechanisms. Stefan highlights the challenge of predicting exact consequences as Earth's magnetic environment and human technology evolve, and notes intriguing correlations between solar wind density fluctuations and seismic activity, adding complexity to understanding Earth-space interactions. The discussion turns to geomagnetic excursions, temporary collapses or weakening of the Earth's dipole magnetic field, versus full reversals where poles permanently switch. During these periods, the magnetic dipole strength drops significantly, sometimes to about 5% of normal, often coinciding with grand solar minima. The increased cosmic radiation influx over extended periods, hundreds to thousands of years, could have profound biological and climatic consequences. Stefan mentions the Lascamp excursion, 42,000 years ago, as an example of weakened field strength, coinciding with extinction pulses and cultural responses, such as the construction of underground shelter systems, interpreted by some as protection from enhanced radiation. Earth's climate history is marked by oscillations like the medieval warm period and Roman warm period, with regional and temporal variability. Stefan references research connecting supernova occurrences to sudden warming episodes, suggesting that extraterrestrial phenomena influence Earth's climate beyond classical Milankovitch orbital cycles. He emphasizes that the Sun is the dominant climate driver, modulating radiation input across the spectrum, but acknowledges terrestrial factors and anthropogenic influences. The recorded climate data remains limited in timescale relative to Earth's geological age, complicating definitive conclusions. Stefan champions an interdisciplinary approach combining geology, geophysics, space weather, and atmospheric science to deepen understanding. He critiques traditional academic silos and acknowledges that his independent YouTube-based research platform allows exploration beyond conventional constraints. He envisions a global observatory integrating geophysical and solar data, independent of political and institutional influences, to democratize understanding and enhance preparedness for natural hazards. A substantial segment covers the nature of plasma, the ionized state of matter dominant in stars and space, with challenging dynamics such as turbulence and magnetic instabilities, complicating nuclear fusion efforts. Stefan explains the difficulties of confining plasma in fusion reactors due to its self-generated magnetic fields and turbulence. He remarks on the mysterious recent death of a prominent MIT plasma physicist investigating turbulence and reflects broadly on the intersections of high-stakes science, secrecy, and potential suppression of transformative discoveries. Electromagnetic signals related to seismic activity, such as earthquake lights and magnetic field fluctuations, possibly indicate electric circuit-like behavior of rocks under stress. He describes how charged igneous rocks under mechanical strain emit measurable electrical signals, sometimes preceding earthquakes, offering potential early warning indicators. Notable historical examples include magnetic anomalies preceding the 1964 Alaska earthquake and enhanced atmospheric conductivity before Bay Area quakes. These underscore a complex interplay of geophysical, electromagnetic, and seismic processes. Stefan discusses the impact of mid-20th century atmospheric and space nuclear testing, which injected charged particles and neutrons into near-Earth space, disturbing the Van Allen belts and producing global-scale electromagnetic effects, including auroras on conjugate hemispheres. He suggests that the legacy of these tests persists within Earth's energetic environment. The guest engages with broader astrophysical concepts, including the structure of the heliosphere, cosmic plasma jets, and the fractal nature of plasma phenomena observed from planetary to galactic scales. He critiques mainstream cosmological theories like the Big Bang and dark matter energy hypotheses as incomplete or overly reliant on theoretical constructs unsupported by observations. He evokes ideas of matter-antimatter symmetry and steady-state universe models proposed by scientists like Hannes Alfvén, advocating for a paradigm shift grounded in laboratory plasma physics and measured cosmic data. The conversation turns to interstellar visitors such as 3I Oumuamua and 3I Atlas, whose properties challenge simple categorization as comets. Stefan highlights 3I Atlas's unusual velocity, narrow jets, potential magnetization, and unusual trajectories, sparking debate about their nature and origin. He critiques simplistic labeling and embraces multiple hypotheses, including magnetically active or solid chunks with different density profiles than typical comets. Mention is made of NASA's imagery limitations, public communication challenges, and speculative extraterrestrial and esoteric narratives that complicate discourse. Stefan explores ancient structures, including the Egyptian pyramids and extensive underground cave systems in places like Turkey. He addresses theories linking these sites to protection during periods of heightened radiation or solar minima, and highlights research into the pyramid's possible function as chemical or metallurgical plants based on geological evidence and ancient technological speculation. Discussions touch on recent remote sensing efforts to detect subsurface features such as potential hidden shafts below the pyramids using satellite radar, with skepticism about data processing and interpretations. The episode contemplates human intuition about geophysical energies embodied in sacred sites and the role of electromagnetic phenomena in historical human culture. Schumann resonances, ultra-low-frequency electromagnetic standing waves at approximately 7 Hz, are detailed as natural Earth resonances generated mainly by lightning. These resonances share frequency and amplitude scales with human brainwaves, suggesting a possible resonance mechanism linking human consciousness with the planet's electromagnetic environment. Stefan speculates on the dissemination of ideas and collective consciousness potentially mediated by these resonances, drawing parallels to Rupert Sheldrake's morphic resonance and acknowledging ongoing research and challenges in empirical validation. The conversation moves into cyclical models of consciousness and history, such as the Yuga cycles from Hindu philosophy, correlated with astronomical precessional cycles. Stefan compares these with historical dark ages and suggests humanity may be ascending from a low consciousness, Kali Yuga, toward greater collective awareness, drawing parallels to ancient knowledge systems and modern energy technologies. Finally, Stefan emphasizes the complexity of climate science, hindered by limited data timescales and politicization. He calls for nuanced understanding, recognizing the sun's dominant influence, Earth's internal dynamics, and anthropogenic factors. Emphasizing openness beyond entrenched ideological divisions, he promotes transparent, inclusive inquiry to advance scientific and societal progress. Stefan closes by noting his independent media presence and educational efforts, encouraging curious listeners to engage critically, pursue interdisciplinary understanding, and contribute to a wider community beyond conventional academic or institutional frameworks.